Amazingly, the buoyant force acting on a hot air balloon is able to lift a basket filled with passengers. This powerful force appears whenever an object is immersed in a fluid. Do you know what fluid this hot air balloon is immersed in? Remember that both liquids and gases are fluids. The fluid surrounding the balloon is air. Let's investigate the buoyant force in another fluid, water. This is a concrete block. This is a wood block, a softwood block, pine actually. I'm going to drop these two blocks into the water in the aquarium. One will sink, one will float. You probably have a prediction about what's going to happen. Let's find out. I suspect your prediction was correct, that the concrete block sinks. When I ask the question, why does the concrete block sink? The answer often is the concrete block is heavier than the wood block. We have to be careful with our vocabulary and understanding here. Consider a cruise ship. More buoyant force. This cruise ship behind me is in fact a huge hotel floating on the surface of the ocean. These huge ships can weigh over 50,000 tons. Despite this huge weight, cruise ships have no problem floating on the ocean. Whether an object sinks or floats is not determined by its weight, but by its density and the density of the fluid it is immersed in.
So one of the things I do, it's kind of a discrepant event, and I'll usually do this after the cans are in the fish tank, but before we've talked about it, is I have two beakers up here. Oh, and I try to make, I try to play with these things. Why did I only fill one of these up? And I get some water, I make sure they know it's tap water. And I should have filled them both up, but I forgot to before class, so I guess I'll just have to fill up the other one. Oh, it's a little higher than this one, and make sure they're the same height. And okay, now they're both full of water. And I have a candle, just an ordinary candle, okay? But I've got two beakers, so I'm going to try to break the candle in half. I want 2 equal sized pieces of candle. Well, I've tried to do this live in front of the students and it doesn't work. You can't break it and be ready to go because it probably you'll fumble with it and it not work. So of course I have a candle already broken in half. I come over here, break the candle, and voila, look what I've done. Oh, that isn't very much in half now, is it? So we talk about that there's a difference in the two sizes of candle. Which one do you think is going to be heavier? They did come from the same candle. Okay, and that's the reason I don't break it ahead of time. I pretend that I'm breaking it here because I want them to understand these are the same candle. There's no difference in them other than size. So they obviously pick that this one's heavier. You can check it if you want. You can have a balance out. And so since it's heavier, it's going to sink. And since this one's lighter, it's going to float. Oh, isn't that wonderful? Okay. Well, all right. But when I take them out, actually I usually have them a little closer together. If I fumble enough, and the kids are used to me fumbling, sometimes on purpose and sometimes accidentally, if I fumble and I drop it, then we've got a problem here. Well, if that happened, what happens if I take this piece of candle and drop it in the other beaker, and it sinks? So now the heavy one is floating, and the light one has sunk. All right, what's happening here? And I wait, and somebody will say something, and somebody will say something else. You tricked us, they're not from the same piece of candle. I pull them out and have a student test them. Believe it or not, the last thing they want to tell me is that they are different liquids. And that is the case. And the point I'm trying to make to them is that it's not the difference in the candles and that makes something float or sink. It's not the difference in the liquids that'll make something float or sink. It's the difference in the density of the floating object and the liquid that you put it into. It's not that this candle is heavier than the other one. It's not that it's more or less dense than the other. It's that the candle, and both of them, are less dense than the liquid they're floating in. And in this case, they're more dense than the liquid they're floating in. So we're comparing the object to the liquid and not to each other. Okay? Little warning here. When I did this to prove that they had a candle, I thought, I should light it because that proves that it's a candle. Fortunately, I didn't do it, so I don't have any horror stories to tell you, but one of these liquids is flammable. So don't prove the candle is real by lighting it, please. They can feel them, they're waxy, so they can prove it that way. Okay? So this is about density of two different liquids compared to the objects that we put in them. Thank you.
What we've just watched there is natural science behaviour of objects in fluids. One of them being the fluid we live in, air. Now watching those, there's no possible way that you would look at those objects in the fluid and think, there's another force there. It must be this gravity. This thing I can't see and is not needed in any way. But yeah, let's add it in. Because that apple fell and it can't be the density of the apple and the density of the air. It can't be that. It's got to be magic. So through natural observations, we can see that things fall through a fluid depending on their density and the density of the fluid. Now, that is it. Nothing else is required unless you want to delve into the world of sophistry. So, we get the why do they fall down? Why do they not fall sideways? Basically, this is when they start handing out the red herrings. And this is the point you say, what object are you talking about? What is it that's fallen to the ground? What is it? An example. But probably if they're playing a game, will be reluctant to give you an example because they know what they're doing. If they don't, they're just indoctrinated and haven't even thought about it. They'll say, what about if and they'll drop the microphone, drop a pen, drop whatever, and it'll fall to the ground. Why is it fallen? Well, because it's more dense than the air that surrounds it. But why does it fall downwards and not sideways? Well, it wasn't in the air to begin with. You picked it up and dropped it. You used your energy. You ate food, had sunlight. The food itself grew through sunlight and nutrients in the ground. It's all transfer of energy. We all know that energy can't be made or destroyed, just transfers through various forms. So you used that energy to lift it up to a height where it shouldn't be, and it returned back to the ground. Equalised. If it fell on mud and it was more dense than mud, it would sink into the mud a little bit. If it's less dense, it'll just sit on top. Well, why do they fall at exact speed? Well, I don't think they do. It's terminal velocity. So, what do things fall through water at the same speed? No, they don't. If it's more dense, it will fall quicker than something that's less dense. And same within the air. If you go up high enough, drop an apple and a cannonball, I'm sure as shit the cannonball will hit the ground first. will accelerate to its terminal velocity quicker and get to the ground first. So when you do an experiment where you're not given enough height, then yes, they'll have a tendency to hit the ground at the same time because you haven't given enough height to give justice to what you're saying. I certainly wouldn't want to believe that I'm living on a spinning ball, just the fact that you haven't got your lazy horse up high enough to prove what you're trying to say. The apple fell from the tree, or the banana, the pineapple, the coconut, because it grew on its tree, its fruit. So it started off as a seed from another tree. Beautifully designed. Nutrients in the ground, the sunlight grows, all the energy is stored in it, lifting it up in the air, branch grows, piece of fruit grows, too heavy for its stalk, back down to the ground. Nothing's in the air to fall. Bird stops flapping its wings. Yes, it will fall. Of course, it has to flap its wings to be up there. No objects are falling due to gravity. Name your object, because I'm sure it's been put up there. Red herrings, nonsense, and we're bored of it. And to think that the character Sir Isaac Newton, who would have been, if he was real, and I'm sure he is, well, who am I to doubt these things, would have been trivium educated. So it's highly unlikely he would have used his foundational knowledge of how to deductively reason, inductively reason, abductively reason, analogically reason, and look at the apple fallen and think, that's gravity. Very unlikely. It's been attached to it, and this is the storyline we're being given. But we've, using our critical thinking now, and realising that it's all bullshit. Anyway, thanks.